Hi, it's Tim. Just wanted to spend some time talking about the Standard Model, which is an ordered list of all the known fundamental particles. Fundamental meaning they have no constituent parts. They're as basic as they can be. The only thing missing from the Standard Model is the graviton, which is the force carrier responsible for gravity, and antimatter. The graviton is, I believe, too weak to be included, and antimatter is simply the opposite to what's already in the table. For instance, all quarks, which is the top left group, have antiquarks, and all the leptons have antileptons, such as anti-electrons, which are normally referred to as positrons. However, the force carriers on the right are an exception and have no opposites, but we'll come to this later. Right, firstly the quarks on the top left are arranged in two ways. To begin with, they get heavier the further right you go, and the quark beneath any in the top row is heavier than the one above it. For instance, the up, which is the U, is lighter than the D, which is the down, and the down is lighter than the charm, which is the C, and the bottom right-hand corner is the heaviest. They are also arranged by charge, the top row having a relative charge of plus 2/3, whilst the bottom row have a charge of minus 1/3. Obviously, quarks don't usually hang around by themselves, but usually form groups of 2 or 3. When they join in groups of 3, they are called baryons. Examples include protons, which are 2 up and 1 down, and charmed double bottom omegas, which are a bit more complicated, but they're just 1 charm quark and 2 bottom quarks. When they form in 2s, they form mesons, which contain 1 quark and 1 antiquark, such as the pi meson, which is a strange and an anti-strange quark, or the pion, which is a up and an anti-down. However, mesons are very unstable and normally have to be made in interactions because they have such short lifetimes. Quarks also have another characteristic called strangeness, which is given by the strange quark. Strange quarks have a relative strangeness of -1, and anti-strange quarks have strangeness of +1. The difference between a quark and an antiquark is simple. Whereas an up quark has a charge of 2/3 and a spin of 1/2, like all fermions, and includes all other quarks, an anti-up quark would have minus 2/3 charge, still the same spin of 1/2, and still the same mass. So beneath the quarks we have the leptons. Now the leptons are much simpler than quarks, and they are simply split into 3 groups or generations. The first group on the left are the electron family, the middle is the muon family, and on the right are the tau family. In effect, it's easier to think of them in rows, as they share more characteristics in periods than in groups. For instance, all of the top row, the neutrinos, which have the Greek V, behave in the same way, and differ only in mass, with the electron neutrinos being the lightest on the left, through to the tau neutrinos on the right, which are the heaviest. Neutrinos are unique as they do not interact with charged particles, and so detecting them is challenging. The bottom row of the lepton family are arranged in the same way, with the electron particle having the lightest, the muon particle being the more massive, and the tau particle being the more massive still. Electrons, muons, and tau particles all have a relative charge of -1 and the same spin, that of a regular fermion, of 1/2. Like the quarks, when you have an anti-lepton, the only difference is the charge. I mean, an anti-electron, anti-muon, and an anti-tau all have a charge of +1. They all have the same spin, obviously, of 1/2, and they all have the same mass as their positive counterparts. But when it comes to antineutrinos, because they have no charge, the charge has to stay the same, and the mass obviously has to stay the same. What happens is the spin gets reversed. So instead of normal neutrinos, which have a left-handed spin of 1/2, like all the fermions, antineutrinos have a spin of 1/2, but right way, as in to the right. And that's the difference between antineutrinos and neutrinos. On the right-hand side of the Standard Model, we have a column which is called the force carriers, or gauge bosons. These are responsible for particle interactions and carrying forces between different particles. At the top is the photon, which is the gamma sign, which is responsible for the electromagnetic spectrum. and is unique in having, well, almost unique in having no mass. So the force can be exerted over long distances. It is hard to understand photons, as they behave both as a wave and as a particle, and this is referred to as wave-particle duality, which was, of course, put forward by Einstein. Below the photon is the G, or the gluon. The gluon is responsible for holding quarks together in baryons and mesons through the strong nuclear force, which is unique to quarks. The gluon also holds protons and neutrons together in atoms and is responsible for all the matter we can see. The gluon also holds protons and neutrons together in atoms and is responsible for all matter we can see. Gluons are required as protons have the same relative electric charge of +1, and so without the gluons they would not be able to bond in the nuclear atums as they would repel each other. Below the gluon are the Z and W bosons. These are responsible for the weak nuclear force, but which boson is used is dependent on the interaction. The Z boson is its own antiparticle, as it has no charge, but the W plus boson is the antiparticle of the W minus boson. W and Z bosons are responsible for altering the charge and spin of particles' interactions, and indeed the W boson can also change the generation, such as changing an up quark to a charm, and because they change the charge and the spin, they also can change particles from being called quarks or leptons to antiquarks or antileptons. The W and Z particles are relatively massive compared to any other particle on the Standard Model, larger indeed than an atom of iron, which has of course a relative atomic mass of 56.